December 28th, 1944. The frozen Belgian countryside trembled as another V-1 flying bomb shrieked toward Allied positions during the Battle of the Bulge. Private Klaus Hoffmann of the Wehrmacht's 15th Army crouched in his foxhole near the village of Bastogne, watching American anti-aircraft guns unleash a thunderous barrage into the winter sky. What happened next would haunt him for the rest of his life, not because of the violence, but because of the impossibility of it. The American shells exploded without touching anything. They detonated in perfect proximity to their targets, ripping through the air with uncanny precision. No direct hits were necessary, no lucky shots required. The V-1 disintegrated mid-flight, and Klaus watched his commanders exchange bewildered glances. In 2 years of brutal warfare, they had witnessed every weapon imaginable, yet this defied comprehension. German intelligence officers had been receiving scattered reports since mid-1944 about a new American defensive capability. Pilots returning from bombing runs over England spoke of flak bursts that seemed guided by unseen hands. Ships reported destroyers whose anti-aircraft fire achieved impossible accuracy rates against Luftwaffe raiders. Initially, High Command dismissed these accounts as exaggeration, the desperate excuses of frightened men watching their comrades fall from the sky. But the evidence became undeniable when Wehrmacht forces overran an American position near Aachen in November 1944. Among the captured equipment, German engineers discovered something extraordinary: artillery shells unlike any they had examined before. These weren't the standard projectiles that required direct impact or timed detonation. These shells contained mysterious glass tubes and intricate circuitry housed within there. Nosecones technology so advanced that even Germany's most accomplished weapons designers stood bewildered before their workbenches. Oberst Heinrich Müller, a decorated officer with the Wehrmacht's weapons testing division, received the first captured shells at a secure facility outside Berlin, according to documentation later recovered by Allied forces. Müller spent 3 days examining the devices before he could even comprehend their basic operating principle. The shells contained miniature radio transmitters and receivers, an engineering marvel so compact and so robust that it could withstand the tremendous forces of being fired from a cannon. As referenced in the post-war technical report, German Evaluation of American Ordnance Technology, published by the United States Army Ordnance Department in 1946, German scientists calculated that these devices experienced acceleration forces exceeding 20,000 times gravity during firing. That any electronic equipment could survive such violence seemed impossible. The technology became known as the proximity fuse. Though German intelligence initially codenamed it Aufschlagsender, Gertia, unbekannt, unknown impact fuse device, its operations seemed almost magical. The fuse transmitted radio waves that bounced off approaching targets. When the return signal reached sufficient strength, indicating the shell was close enough, the fuse triggered detonation. This meant shells could destroy aircraft by exploding nearby, rather than requiring direct hits, a revolutionary advantage that improved kill rates by orders of magnitude. What the Germans didn't know, what they couldn't have known, was that this single invention represented one of the most closely guarded secrets of World War II, protected with security measures rivaling even the Manhattan Project. January 9th, 1945. Dr. Werner Heisenberg stood in a converted factory workshop in Thuringia, examining photographs of the captured American fuse components spread across a metal examination table. The brilliant physicist, already famous for his contributions to quantum mechanics, had been pulled from uranium research to analyze this unexpected technological prize. Behind him, 3 of Germany's finest electrical engineers waited in nervous silence, knowing their assessment would reach the highest levels of the Reich within hours. Heisenberg lifted one photograph showing the miniature vacuum tubes, no larger than a pencil eraser. His hands trembled slightly, though whether from cold, exhaustion, or professional awe, none of the assembled scientists could determine. These tubes represented manufacturing precision that exceeded anything German industry had achieved. The entire mechanism had to function reliably after being subjected to forces that would pulverize conventional electronics into dust. General Hermann Göring demanded answers when the technical reports reached his desk. The Luftwaffe was hemorrhaging aircraft at unsustainable rates, and if the Americans possessed weapons that could shoot down German planes without direct hits, the already deteriorating air war would become completely unwinnable. He ordered an immediate crash program to reverse engineer and duplicate the American technology. But Germany's scientists encountered obstacles at every turn. The vacuum tubes required glass-to metal seals of extraordinary quality seals that Germany's struggling industrial base could no longer manufacture reliably. The electrical components demanded materials that had become scarce or completely unavailable due to Allied bombing campaigns and resource shortages. Most critically, the precision miniaturization required manufacturing tolerances that German factories, even in optimal conditions, would need months or years to achieve. Dr. Rudolf Kachan, an electrical engineer from Siemens, who had been conscripted into weapons research, spent 6 weeks attempting to recreate just the radio frequency oscillator circuit, according to his personal diary, covered decades later and referenced in the 1978 historical volume The Secret War, Spies, Ciphers, and Guerrillas. Kachan wrote, "We are children playing with adult toys. Every component reveals new depths of sophistication we cannot match. Americans have achieved what we believed impossible." The Germans discovered that the proximity fuse employed something called printed circuit, a manufacturing technique where electrical pathways were chemically etched onto flat boards rather than hand-wired. This process, largely unknown in Europe, allowed for consistent, reliable production of complex circuits. German attempts to hand-wire equivalent circuits resulted in devices too fragile, too large, or too unreliable to survive the firing shock. Meanwhile, the strategic implications became increasingly clear. Intelligence reports indicated that American forces were now using proximity fuse shells across multiple theaters. Naval vessels protecting convoys in the Atlantic were decimating U-boat-launched V-1 attacks. Anti-aircraft batteries surrounding England made Luftwaffe bombing runs suicidal endeavors. Ground forces used proximity fuses against concentrated infantry formations with devastating effectiveness, shells that burst overhead, showering enemy troops with shrapnel from angles that traditional explosives couldn't achieve. Colonel Johann Richter, a Luftwaffe intelligence analyst, prepared a classified assessment in late January 1945. Its report, captured intact by American forces advancing into Germany, concluded with a stark warning: the enemy possesses technological capabilities we cannot counter with available resources. Their industrial capacity and scientific innovation have achieved what we believed would require another decade of development. We are fighting an opponent who has fundamentally altered the mathematics of aerial warfare. September 3rd, 1940. Dr. Merle Tuve stood in a cramped laboratory at the Carnegie Institution in Washington, District of Columbia, examining the shattered remains of yet another failed prototype. Physicists had been wrestling with an impossible problem for months: how to create a miniature radio transmitter and receiver that could survive being fired from a 5-inch naval gun while remaining sensitive enough to detect aircraft at ranges sufficient for effective detonation. The British had approached the Americans with desperate urgency earlier that year. The Luftwaffe was pounding England's cities with aerial bombardment, and conventional anti-aircraft fire was proving woefully inadequate. Gunners had to estimate range, speed, and trajectory, then set mechanical time fuses, hoping their calculations proved accurate. Hit rates rarely exceeded 2%, meaning that 98 out of every 100 shells fired accomplished nothing except noise and expense. British scientists had been experimenting with photocell-based proximity fuses, devices that would detect sudden changes in light when passing near a target. But these systems proved unreliable in varied lighting conditions and useless at night. They needed something better, something revolutionary. American ingenuity might provide the answer that British research had failed to deliver. Tuve assembled a team that included some of America's brightest scientific minds. Dr. Lawrence Hafstede, Dr. Charles Lauritsen, and a young engineer named Harry Diamond joined the effort, which operated under the innocuous designation Section T of the National Defense Research Committee. Security protocols matched those of the most classified military programs. Researchers couldn't discuss their work with family members, couldn't publish findings, couldn't even acknowledge the project's existence to colleagues outside their immediate team. The technical challenges seemed insurmountable. The device needed to be small enough to fit inside an artillery shell's nose cone, leaving room for the explosive charge. It needed to survive acceleration forces during firing that would exceed 20,000 Gs. It needed to function reliably in temperatures ranging from Arctic cold to desert heat. It needed to be manufactured by the thousands, eventually millions, using assembly line techniques that could maintain quality control across multiple factories. And crucially, it needed to cost little enough that firing dozens of shells at a single target remained economically feasible. The breakthrough came through a combination of innovations. Researchers developed ruggedized vacuum tubes by filling them with gel that dampened vibrations without interfering with electrical properties. They created the fuse's power supply using a tiny generator system where the shell's rotation during flight caused a spring-loaded rotor to spin, generating electricity. As documented in the technical history compiled by the United States Naval Ordnance Laboratory in 1947, this eliminated the need for batteries, which couldn't survive the firing shock. By December 1940, the team had produced a working prototype. The first successful test occurred at Dahlgren Proving Ground in Virginia. 5-inch shell fired at a radio-controlled target drone. The shell exploded 20 feet from the aircraft, close enough that shrapnel would have destroyed it in combat conditions. The assembled observers, including senior Navy officers and National Defense Research Committee officials, watched in stunned silence before erupting in celebration. But creating a laboratory prototype and manufacturing millions of combat-ready fuses represented entirely different challenges. The project expanded to include Western Electric, Eastman, Kodak, Raytheon, and other major manufacturers. Production lines had to be established, workers trained, quality control systems implemented. Part 4. Production Miracles and Security Obsessions. March 17, 1942. The Eastman Kodak factory floor in Rochester, New York, hummed with activity as hundreds of workers, many of them women, newly recruited to replace men drafted into military service, assembled proximity fuses at workstations that stretched the length of a football field. None of them understood what they were building. Security protocols ensured that each worker completed only specific, isolated tasks, never seeing the complete device or comprehending its ultimate purpose. Martha Reynolds, a 23-year-old former schoolteacher from Buffalo, spent 8 hours daily soldering connections to miniature vacuum tubes that arrived at her station in sealed containers. She connected wires following detailed diagrams, inspected her work under magnification, then passed the partially completed assemblies to the next station. She had no idea whether she was building radio components, telephone equipment, or something else entirely. Questions were discouraged. Curiosity was considered a security risk. The scale of production proved staggering. By 1943, American factories were producing over 40,000 proximity fuses daily. This required innovations in manufacturing techniques that had never been attempted at such scale. The miniature vacuum tubes alone represented a technical marvel. Each tube was approximately the size of a man's thumb, yet contained all the components of a standard radio tube: filament, plate, grid, glass envelope, and precisely engineered connections. These tubes had to function reliably after experiencing acceleration that would turn conventional vacuum tubes into glittering powder. General Leslie Groves, who would later oversee the Manhattan Project, toured a fuse production facility in April 1942. He later remarked that the security measures impressed him more than the technology itself. Every component was tracked through serialized documentation. Workers couldn't bring briefcases, cameras, or personal bags into production areas. Guards inspected lunchboxes. Telephone conversations were monitored. Even the industrial waste was collected and incinerated under armed supervision to prevent any fragment of a partially completed fuse from falling into enemy hands. The obsessive security stemmed from a terrifying awareness. If the Germans captured an intact proximity fuse and successfully reverse-engineered it, they could use the technology against Allied bombers over Europe. A single B-17 Flying Fortress carried 10 crew members and represented months of training and hundreds of thousands of dollars in equipment. Anti-aircraft batteries suddenly became 5 times more effective. The strategic bombing campaign would become unsustainably costly. According to documentation referenced in the 1984 scholarly work, The Secret Science of Wartime Innovation by historian Stephen McFarland, American military intelligence implemented extraordinary measures to prevent fuse capture. Proximity fuse shells were initially prohibited from use over land, where unexploded rounds might fall into enemy hands. Naval vessels could use them freely. A dud falling into the ocean would sink beyond recovery. The fuses were first deployed in combat during the Battle of Santa Cruz in October 1942, where the cruiser USS Helena used them against Japanese aircraft attacking American carriers. The results exceeded even optimistic projections. The Helena's gunners reported hit rates of approximately 40%, a 20-fold improvement over conventional time-fused shells. Japanese pilots, accustomed to dodging anti-aircraft fire by making evasive maneuvers after seeing shell bursts, suddenly faced explosions that didn't require direct hits. The psychological impact proved as significant as the physical destruction. Japanese aviators reported that American ships seemed protected by new defensive weapons they couldn't comprehend or counter. But the security protocols created operational frustrations. Ground forces in the Pacific and European theaters knew that proximity fuses existed and demanded access to this technology that could revolutionize artillery effectiveness. Commanders argued that the tactical advantages outweighed security risks. Especially as the war progressed and Allied victory seemed increasingly certain. The breakthrough came through policy changes rather than technology. By mid-1944, with Allied forces firmly established in France following D-Day, restrictions on ground use were partially lifted. January 24, 1945. Dr. Walter Trinks, a physicist who had spent the war years developing infrared detection systems for Wehrmacht night fighters, sat in a stone building near Magdeburg, writing a report that would seal Germany's technological fate. Before him lay the disassembled components of 3 captured American proximity fuses, the most complete specimens German forces had recovered. After 6 weeks of intensive analysis, his conclusions were devastating. Trinks wrote with clinical precision. But his underlying message was unmistakable. Germany could not replicate this technology with available resources, manufacturing capacity, or time. Even if granted unlimited funding and materials luxuries that the crumbling Reich could no longer afford, German industry would need at least 18 months to establish production capabilities. By then, the war would be decided. The vacuum tubes alone represented an insurmountable obstacle. Trinks calculated that each tube's glass envelope had wall thickness variations of less than 0.02 of an inch. German vacuum tube manufacturers, using existing techniques, achieved tolerances of approximately 0.08 of an inch. This seemingly minor difference became critical under the tremendous forces of artillery firing. German-manufactured tubes would shatter. The report documented 27 distinct innovations embodied in the American fuse design. The printed circuit boards, the gel-stabilized vacuum tubes, the centrifugal power generator, the radio frequency oscillator circuit that remained stable across temperature extremes, the mechanical safety features that prevented accidental detonation. Each innovation individually represented significant engineering achievement. Together, they comprised a technological leap that German scientists struggled to comprehend. Major Hans Kamaro, a Luftwaffe technical intelligence officer, forwarded Trinks's report to Reichsmarshal Gring with an accompanying assessment. According to records captured by Soviet forces and later shared with Western allies, Kamara wrote, "The Americans have demonstrated manufacturing and engineering capabilities that exceed our projections by 5 to 10 years. They have achieved mass production of devices we consider laboratory curiosities. This suggests their industrial capacity and technical education systems have evolved beyond our understanding." The psychological impact on German military leadership proved profound. For years, Nazi propaganda had emphasized Aryan technical superiority and German engineering excellence. The proximity fuse shattered these comfortable assumptions. Here was incontrovertible evidence that American scientists and engineers had not only matched but decisively surpassed German capabilities in a critical military technology. Colonel Erich Schneider, who commanded anti-aircraft defenses around Berlin, requested a classified briefing on the American fuses in February 1945. According to testimony he provided 2 Allied interrogators after Germany's surrender, the briefing left him shaken. "We were told that every B-17 bomber attacking our cities was protected by weapons we couldn't replicate. Our fighters were being destroyed by flak shells that didn't need to actually hit them. I realized we were fighting an enemy who was innovating faster than we could respond. German attempts to develop countermeasures proved equally futile. Engineers proposed using aluminum chaff strips of metal foil dropped from aircraft to confuse radio-based detection systems. But the proximity fuses, operating frequency, and signal processing were designed to reject such interference. Captured technical documents showed that American engineers had anticipated German countermeasures and incorporated defensive features into the original design. Luftwaffe pilots reported that American anti-aircraft fire had become so effective by early 1945 that daytime bombing missions were effectively suicide runs. Major Johann Steinhoff, a decorated fighter ace, later recalled, "We knew American gunners had some new weapon. Shells would explode in precise proximity to our aircraft with uncanny consistency." Pilots who survived reported seeing black bursts appearing as if guided by supernatural forces. It felt like fighting an opponent who could see through fog. These strategic implications extended beyond immediate tactical defeats. German intelligence analysts recognized that if America could develop, produce, and deploy such sophisticated weapons while simultaneously fighting across multiple global theaters, the underlying economic and industrial capacity must be truly extraordinary. May 2, 1944. Lieutenant Robert Morrison stood on the deck of the destroyer USS Fletcher in the South Pacific, watching his ship's 5-inch guns engage a formation of Japanese Betty bombers approaching at 12,000 feet. The shells left white smoke trails as they climbed, and blossomed into perfect spherical clouds of shrapnel exactly where the bombers flew. 2 aircraft disintegrated immediately. A third staggered, trailing smoke, before plunging into the ocean. Morrison had served in the Pacific since 1942 and remembered the early desperate months when Japanese aircraft seemed to attack with impunity. American gunners would fire hundreds of shells at approaching bombers, hoping for lucky hits that rarely came. The mathematical probability of actually striking an aircraft with a time-tuned fuse shell was approximately 1 in 5,000. Now, with proximity fuses, that ratio had improved to approximately 1 in 15, a 300-fold improvement in lethality. The technological advantage extended across every theater where American forces operated. In the English Channel, Allied ships protecting the D-Day invasion fleet used proximity-fused shells to create an impenetrable defensive barrier against Luftwaffe attacks. According to the official United States Strategic Bombing Survey published in 1946, German aircraft losses over the invasion beaches exceeded 80%, an unsustainable attrition rate that effectively eliminated the Luftwaffe as a meaningful factor in the Normandy campaign. Captain James Saunders commanded an anti-aircraft battery outside Antwerp in December 1944, when German forces launched their final desperate offensive through the Ardennes forest. His unit received priority allocation of proximity-fused shells with specific orders: deny German forces any aerial reconnaissance or close air support. For 3 weeks, his guns fired continuously at any aircraft approaching Allied positions. The psychological impact on German pilots proved as devastating as the physical destruction. Luftwaffe veteran Ernst Reinhardt testified after the war, "We called the new American shells Hexenfeuer, witchfire. They seemed intelligent, as though they knew where we would fly before we knew ourselves." Pilots refused missions. Those who did fly rarely returned. The Americans had created a defensive wall we couldn't penetrate. The technology's effectiveness increased as American forces gained experience. Gunners learned optimal firing solutions. Fire control systems were refined. Radar-directed guns combined with proximity fuses created lethal zones where aircraft survival became nearly impossible. Japanese kamikaze pilots, desperate attackers willing to die destroying Allied ships, found even their suicidal tactics countered by weapons that didn't require direct hits to shred aircraft into falling debris. Admiral Chester Nimitz, commander of Pacific Naval Forces, wrote in a classified assessment in March 1945. "The proximity fuse has revolutionized naval anti-aircraft defense. Ships that would have been vulnerable to aerial attack can now defend themselves with unprecedented effectiveness. This technology has fundamentally altered naval warfare's strategic calculations." But perhaps the most significant impact came in Europe's ground war, where proximity fuses transformed artillery from a weapon requiring direct hits or lucky timing into an area denial system of terrifying efficiency. Shells that burst 20 to 30 feet above enemy positions showered troops with shrapnel from overhead angles that trenches and foxholes couldn't protect against. German soldiers called them Baumdurch, to tree bursters, because shells would detonate above forest canopies, killing troops who believed themselves concealed. Traditional artillery required shells to hit trees directly or detonate on contact with the ground. Proximity fused shells exploded at optimal height automatically, turning forests from cover into killing zones. Corporal Heinrich Bauer of the Wehrmacht's 6th SS Panzer Army survived the Battle of the Bulge and surrendered to American forces in March 1945. During interrogation, he described the impact of proximity-fused artillery. "We heard the shells coming, the same whistle as always. But they exploded above us, not on impact. Shrapnel fell like metal rain. Foxholes offered no protection, and died without cover to hide behind." August 6, 1944. Commander David Ingalls, a naval aviator aboard the carrier USS Enterprise, watched from his Hellcat fighter as Japanese bombers attempted to attack the task force steaming toward the Philippines. The American ship's anti-aircraft fire created a wall of explosions that tore through the Japanese formation like a threshing machine. Within 90 seconds, 17 of the 20 attacking aircraft fell, burning into the Pacific Ocean. Ingalls had flown in the Battle of Midway, where Japanese aircraft nearly succeeded in sinking multiple American carriers despite fierce defensive fire. Now, 2 years later, the mathematical equations of aerial combat had been fundamentally rewritten. Proximity-fused shells transformed American ships from vulnerable targets, requiring fighter protection, into floating fortresses capable of defending themselves against massed air attacks. The Japanese military leadership struggled to comprehend what had changed. Admiral Tokijiro Onishi, architect of the kamikaze strategy, knew that Japan's industrial capacity could no longer replace aircraft and trained pilots at rates matching American attrition. The kamikaze program represented a calculated gamble: use aircraft as guided missiles piloted by willing martyrs. If conventional attacks couldn't penetrate American defenses, perhaps suicidal determination could succeed where tactical sophistication had failed. The proximity fuse defeated even this desperate strategy. Kamikaze pilots couldn't evade shells that detonated automatically at optimal range. Their willingness to die became irrelevant when American gunners didn't need direct hits to destroy approaching aircraft. Japanese attackers died hundreds of yards from their targets, shredded by shrapnel clouds that anticipated their flight paths with mechanical precision. Lieutenant Commander Tadashi Nakajima survived 3 kamikaze missions, an almost impossible feat, before being too severely wounded to fly. During post-war interviews conducted by American historians and referenced in John Keegan's 1989 military history, the Second World War, Nakajima described the futility. "We approached American ships knowing we would die. That was acceptable. We were prepared for honorable death. But we died achieving nothing. The American guns destroyed us before we could reach our targets. We became falling debris, not avenging warriors." The technological advantage extended beyond naval combat. American bombers attacking Japanese positions throughout the Pacific used proximity, fused bombs that detonated at optimal altitude above target areas. Japanese troops, accustomed to taking shelter in bunkers and foxholes during bombing raids, discovered that their defensive positions offered minimal protection against weapons that exploded overhead before impact. General Tomoyuki Yamashita, commanding Japanese forces in the Philippines, sent a classified report to Tokyo in November 1944, describing American artillery capabilities. The report, captured by Allied forces advancing through Manila, stated, "The enemy possesses explosive shells that detonate without requiring direct impact or visible targets. These weapons have rendered conventional defensive fortifications obsolete. Troops cannot shelter effectively. Casualties from artillery bombardment have increased by estimated 300%. Marine Corps commanders in the Pacific requested maximum allocation of proximity-fused ammunition for operations where Japanese forces occupied fortified positions. The battles for Iwo Jima and Okinawa demonstrated the technology's devastating effectiveness against entrenched defenders. Artillery barrages could neutralize Japanese strongpoints without requiring direct hits on specific bunker shells that burst overhead, suppressed or killed defenders who believed themselves protected by concrete and earth." The strategic implications became clear to Japanese military leadership by early 1945. American technological superiority wasn't limited to industrial capacity or numerical advantages. The United States possessed weapons that operated on principles Japanese engineers couldn't immediately replicate. This wasn't a question of resources or manufacturing scale, it was fundamental scientific innovation that Japan's wartime economy and educational system couldn't match. Emperor Hirohito, in meetings with military advisors in June 1945, expressed concerns about the growing technological disparity, according to historical records preserved in the Japanese Imperial Archives. He questioned whether continuing the war made strategic sense when the enemy demonstrated such overwhelming advantages in military innovation. September 16, 1945. Dr. Werner Ozenberg, who had coordinated much of Nazi Germany's wartime scientific research, sat in an American interrogation facility outside Frankfurt, reviewing technical documents that Allied intelligence officers had placed before him. The documents detailed the complete development history, manufacturing processes, and deployment statistics of the American proximity fuse information that had been among the war's most closely guarded secrets. Ozenberg read in silence for nearly 40 minutes before looking up at his American interrogators. His first question, delivered in precise English, was simple. When did you begin this program? When told that initial development had started in 1940 and mass production had begun by early 1942, Ozenberg sat back in his chair, visibly shaken. We believed you were years away from such capabilities. This explains much. The post-war technical assessments conducted by German scientists for Allied intelligence revealed the depth of Germany's technological miscalculation. According to the comprehensive report, German reactions to American technological superiority, compiled by the United States Army Historical Division in 1947, German researchers estimated that replicating the proximity fuse would have required at minimum 3 years of focused development and the establishment of entirely new manufacturing processes. Even then, success wasn't guaranteed. The mathematical impact of the proximity fuse on the war's outcome proved staggering. American military statisticians calculated that proximity-fused anti-aircraft shells achieved approximately 5 times the effectiveness of conventional time-fused shells. This translated directly into saved lives: fewer ships sunk, fewer aircraft lost, fewer ground troops killed by enemy air attacks. In the Pacific Theater alone, naval analysts estimated that proximity fuses prevented at least 60 ship losses and saved thousands of sailors' lives. General George Marshall, speaking at a classified briefing in October 1945, called the proximity fuse one of the 3 most important technological developments of the war, alongside radar and the atomic bomb. He noted that while radar and the atomic bomb received more public attention, the proximity fuse had saved more American lives than any other single invention of the war years. British Prime Minister Winston Churchill, writing in his post-war memoirs, described the proximity fuse as a technology that proved as crucial to victory as any weapon developed during those desperate years. The Americans achieved what many of our finest scientists believed impossible. They created magic that looked like engineering. The security restrictions that had surrounded the proximity fuse during wartime were gradually relaxed after Germany and Japan's surrender. Scientific publications began appearing in 1946, detailing the development process and technical innovations. Engineers around the world studied these documents with fascination, recognizing that American researchers had achieved breakthroughs in miniaturization, ruggedization, and mass production that would influence countless post-war technologies. The proximity fuse's innovations found applications far beyond military uses. The techniques developed for manufacturing reliable electronic components under extreme conditions accelerated the development of transistors, integrated circuits, and eventually the entire consumer electronics industry. The quality control processes established in proximity fuse factories became models for post-war manufacturing across multiple industries. Japanese Admiral Matomu Ugaki, who had commanded kamikaze operations during the war's final months, reflected in his diary, discovered after his death, and referenced in American historian Richard Frank's 1999 book, Downfall: The End of the Imperial Japanese Empire. We fought bravely, but we fought blindly. The Americans possessed weapons we didn't know existed. We sacrificed thousands of pilots attacking ships protected by technology we couldn't comprehend. History will judge whether such sacrifice was heroic or merely futile. The proximity fuse represented more than technological achievement. It embodied the industrial, educational, and scientific systems that produced such innovations. American universities had trained the physicists and engineers who designed the fuse. American corporations possessed the manufacturing expertise to produce millions of units with consistent quality. American workers, including thousands of women who entered industrial workforce during wartime, assembled components with precision that made mass production possible. In the decades following the war, as historians analyze the conflict's turning points. The proximity fuse emerged as a case study in how technological innovation could decisively influence military outcomes. The Germans had captured the devices, studied them intensively, and admitted they represented capabilities beyond their ability to replicate. That acknowledgement, more than any battlefield defeat, confirmed the technological supremacy that would define America's post-war global position. The story of the proximity fuse remained largely unknown to the general public for years after the war. Security classifications kept details secret well into the 1950s. But within military and scientific communities, the achievement was recognized as revolutionary, a demonstration of how focused research, adequate funding, manufacturing excellence, and operational security could combine to create weapons that altered warfare's fundamental mathematics. Private Klaus Hoffmann, the German soldier who had watched American shells explode with impossible precision during the Battle of the Bulge, survived the war and eventually emigrated to the United States in 1952. In interviews conducted decades later, he recalled his first encounter with proximity-fused shells. "We knew in that moment we were fighting an enemy who had surpassed us, not just in numbers or resources, but in imagination and capability. They had created something we never imagined possible."